Welcome to Everything STEAM. I'm your host, Sam Stanford. As a physicist and structural engineer with Jacobs Engineering, I've made many connections with some bright individuals who are either working, studying, or self-taught and passionate about our particular topics of discussion. First of all, apologies for the delay. It has been quite a personal transition for me since moving from the United States to Tel Aviv-Yafo, Israel. It took over 3 weeks, honestly, to get all of my personal things, including my podcasting equipment, and I didn't want to record unless I had the proper equipment. But I'm back. This episode is geared towards the cutting edge of physics with a sprinkle of Particle Physics 101. My guests and I have planned 3 specific topics that are categorized as a current mystery and or asymmetry. And an asymmetry is the lack of equivalence between parts or aspects of something. So, for example, a common asymmetry is the amount of right-handed people in society compared to left-handed people. But we will start out by building your understanding of the standard model of particle physics, and then, of course, explain the current research and issues or holes with it. And then, with that knowledge, we will dive into the asymmetry of matter and antimatter, and wrap up with a topic that my guest is very familiar with, ultracold neutrons. Ooh. So, speaking of my guest, I would like you to please meet Dr. Kevin Hickerson. Kevin is a nuclear physicist specializing in probing the fundamental symmetries of nature using ultracold neutrons. He possesses a bachelor's, master's, and doctorate in experimental physics from the California Institute of Technology in Pasadena, California, or Caltech. Kevin is also the host of the science and comedy podcast Surely You're Joking, which features comedians like Jimmy O. Yang, Mitch Burrow, Owen Benjamin, Griff Pippin, and former guest star of this podcast, Matthew Broussard. My favorite fact about Kevin is that he has a dozen patents in 3D printing, robotics, tablet computing, machine learning, optics, and solar energy. So, now that you've been introduced to Kevin and the topic of this podcast, we're going to head into our first segment where we plan to talk about the standard model of particle physics and, of course, its limitations. Cheers. Kevin, welcome to the podcast. How you doing?
Good. Thanks for having me.
Yeah, absolutely. It's been a long time coming. I think we met 2 months ago about this.
Yeah, a long time. Yeah, we finally made it work. So that's good.
Yeah, absolutely. So what's new in the world of Kevin right now?
Well, I'm currently traveling, so it's fun to do this interview while I'm traveling. I'm in Las Vegas, which is fun. I was traveling for work. I was just at the Advanced Nuclear Conference in Nebraska, and that was really awesome. I met the governor of Nebraska. I got to talk to a lot of business leaders and energy people who deal with energy. So, and that's mostly what I'm working on right now. I'm trying to develop a company I'm working with, or that I started. Not working with. I started to use nuclear energy to do some cool things.
So. Oh, that's awesome. We definitely need that in this country. I think right now there's only one new nuclear site that's in construction at the moment, but yet there's if you look at it internationally, China has 27 that are currently in motion.
Yeah. So the Vogtle plant in Atlanta was just completed, and that's a really big accomplishment, but that took a lot of effort, and it was almost canceled many, many, many times. So we talked about that a lot at the conference, but so it's a big accomplishment. What we're really focused now in the US at the moment is advanced nuclear, and specifically small modular reactors, which are reactors that are much smaller than traditional plants, and we're really hoping that will stop the delays and the construction problems that traditional reactors have had, and they're also going to be safer and cheaper and awasomer. So
we love to hear that. It's safer, cheaper, and awesomer. Absolutely.
I'm not sure that's the official term, but I'm gonna use it.
It's something that's been talked about for a long time, and it's actually great to hear that it's coming into fruition. So I mean, we're not here to talk about nuclear energy.
Fair enough.
We're going to be talking about particles, really. But this first segment, we want to talk about the standard model of particle physics, and then weirdly, with this podcast, we don't typically do podcasts like this because we're typically putting science and engineering, tech, etc. on a pedestal, saying all the great achievements and everything. But here we're gonna. Obviously, the standard model is a wonderful achievement. It gives us a lot of information, and but we're also going to
It's
be
the
poking holes at it a little bit,
uh
or displaying the holes that are in the standard model. And then also, as we move through the episode, we'll also be kind of bringing up things that are, I guess, mysteries or that are being worked on. It's just a totally different approach to the podcast, which is pretty exciting. Yeah. So the first segment, we're going to talk about the standard model. So we might as well just jump right in, and I guess I'll ask you the really bland question to start out. What is the standard model, and what are the major groups in the standard model?
All right. Well, let's start with the first part. So, the standard model has a really boring name, but in a weird way, it is both boring and it's also really awesome. Just like nuclear power. Standard model is actually the most successful scientific theory, mathematically, the most successful scientific theory in human history. It's some parts of it are accurate to 40 decimal places, meaning that you can calculate something down to 40 decimal places. Just so you know, we don't even have the ability to calculate the mass of the sun to about 4 decimal places or 5 decimal places, something like that. So even though gravity is also a great theory, there's some things that we don't know about the universe that we nearly as well as we understand the standard model. And that's been a really good blessing and also a curse. And so the blessing is that we really understand what happens with particles almost all of the time. Almost all of the time. And that, especially in electromagnetism, we understand electromagnetism, which is a part of the standard model. It's actually just one little piece of it. So that means everything having to do with light, with charge, with electrons, all of that's one tiny corner of the standard model, and then and that's the best understood or best measured. And then inside of that, we also understand everything that almost everything. I always do say almost. We understand almost everything that happens with protons, with neutrons, and then there's an entire zoo of particles that we can only make in a particle accelerator, and we didn't even realize were there until the 1960s and 1970s. And then so that's the nice part. The downside is that it's very frustratingly wrong about other things, and I think that's the main thing we're going to talk about, is that something that still just cannot explain, despite being this incredibly accurate and successful scientific theory, it just doesn't explain certain things.
Oh yeah, yeah, most definitely. And the standard model can be broken down into 2 major groups. And correct me if I'm wrong in any of this, but the fermions and the bosons. The fermions are the mass particles, and then the bosons are the force carrying particles. If you want to jump into that a little bit more.
Sure. So both fermions and bosons are part of a subset of what the standard model is a part of, which is quantum mechanics, and specifically quantum field theory. So if you're like a Venn diagram or something, there's quantum mechanics, which explains all of quantum material. That's also a very unbelievably accurate theory in the sense that we've never found a case where it's wrong, except it still is wrong some of the time. But other than that, every particle in quantum mechanics, especially when you start making particles in quantum mechanics, you make fermions which have spin 1/2, which is a very weird property that is not easy to explain in terms of everyday objects. It's not like if you spin a bowling ball, that is not that in no way acts like a spin 1/2 particle.
Yeah.
That's a classical object, and so we have a lot of trouble understanding it intuitively. But most of us we are made of spin 1/2 particles. So that's all fermions are described that way. They're named after Enrico Fermi because he first helped describe these early on when he was working on quantum mechanics. Then, as you said, so almost anything with mass that we know of, except for one particle, is a fermion. I said except for one because the particle that gives mass to everything is actually a spin 0 particle. So that was only discovered recently. That's called the Higgs boson. Well, no, sorry. There's 2 others that have mass. Sorry. I should have jumped to that. There's actually force carrying particles that also have mass that couple to the Higgs boson. have to do with the weak nuclear force. See, I don't want to actually start from the back. I want to go the other way. So we need to back up a little bit. We'll get into that later. So
Mhm.
the bosons have spin 1, and almost all interactions, meaning like when two particles talk to each other, they use a boson to talk to each other. That is, so a fermion is coming along, and then a boson is in exchange between the two. It's almost like a little messenger that says, I have this charge, I have this spin, I'm here, I'm going this speed, and it transmits to the other particle and then goes off. And that's how the Standard Model describes how pretty much everything in the universe interacts. I say
Right.
almost everything because one thing missing from the Standard Model is gravity.
Right. Like
Gravity,
I was going to say that actually, it's
yeah,
the force carrying particles deal with 3 of the 4 fundamental
yeah.
forces. Yeah.
Yeah, and yet even though gravity is the weakest force, it's also the most important on a big scale because it becomes the strongest when you're talking about the universe and the Big Bang and stuff like that.
Right.
And unfortunately, gravity is not in the Standard Model. And there's a lot of really interesting reasons why it's not. People have tried over and
Hmm.
over and over, starting with Albert Einstein. He went to his deathbed hoping he could figure out even before he didn't even get to find out all of the Standard Model, but it doesn't change the fact that he tried to make gravity and quantum mechanics work together, and they just don't work together. And that's a
Yeah.
very deep mathematical problem.
Yeah. 100%. The Standard Model can get extremely deep. Like what we're just talking about right now is just breaking down the fermions and the bosons, but like it gets more intricate based on like the particle's properties. And then also, we haven't even mentioned antimatter. There's a whole nother set of particles that run with the Standard Model.
You want me to try and name the particles? I could try off the top of my
Uh,
head. No, I can. I mean, we mentioned fermions.
mhm,
Let's start there. So there's actually a lot of fermions. Most of them don't occur in everyday life, but some of them do. So the ones that you and I are physically made out of all the time
mhm.
are up quarks and down quarks and electrons and
Yep.
photons. And then finally just throw some fun in a thing called a gluon. That's what you and I are made of all the time. So
Mhm.
just all of the mass in your body where you're feeling yourself existing, that's what is causing that to exist. Those are according to the Standard Model, those are those fundamental particles. We've never found anything smaller than those. And that's kind of weird because those don't sound very recognizable to most people because most people don't like say, "Oh, I'm made of up and down quarks," but that's actually is what you are made of. That is
Yep.
like when you feel that weight of you holding down on Earth. Ironically, even though gravity is not included in the Standard Model, that weight is mostly up and down quarks and gluons, and electrons play a little bit of a role in there too, but they mostly just do everything related to chemistry. So up and
Mhm.
down quarks make up neutrons and protons. That I'm sure everyone's heard of. You heard about that in chemistry class, but those are neutrons and protons are not fundamental. They're just made up of these quarks inside, and they're glued together. That's why they're called. There's this particle called a gluon that glues up and down quarks together. Flash, flash
We
another seed or something.
we're good. We can just say, oh, we're back from technical difficulties.
Yeah,
No worries. But we were talking about the different particles in the fermions, and you were alluding to the things that make up everyday life as we see it, unless we're making it an accelerator, or maybe even somewhere where it's extremely hot and dense, like even like a neutron star. But what is within our grasp would be more like what we make in the particle accelerators.
right.
Um,
Yeah. So in addition, once we discovered up and down quarks, we thought we had everything. We really did. And this has happened a lot throughout history. We thought we understood everything, and then something very strange happened, and that actually happened in Pasadena, California, which is where I went to school. So it was a cool place for it to happen. It happened
nice.
on the top of a mountain, where we suddenly discovered this thing raining down from space, and it was a lot heavier than something that could be explained by up and down quarks or by protons and neutrons. And it was this weird particle called a kaon, which I like because my name starts with K, so I think it's just cool. But but it was these weird kaons showed up, and they didn't behave like something that could be explained by stuff that was inside of the rest of matter. And the way it eventually got explained is that somebody said, I bet there's a new kind of quark, and I bet that quark is called a strange quark. And they called it strange because, quite frankly, it was strange.
Yeah.
It behaved just like a down quark in a lot of ways, except it was strange. And it was strange in that it weighed more. That was the only thing about it. It just weighed more. It was
Interesting.
just heavy. It was a down quark, but it weighed more, and it only appeared in this type of things, and it only lived for a very short amount of time. And that really, that really is what I would say. That's when I don't know exactly when the term standard model came up, but that was definitely when people said, okay, we actually need a model to we need a theory that explains what these particles are, what was going on. Especially the fact that they were raining down from space was particularly weird. So or strange. Sorry.
Yeah.
And so so this particle is added, but then people were said really quickly a pattern showed up to say, well, why is there a heavy down quark whereas there's an up and down quark? Shouldn't there be something just like the up quark? And that was the first time that the standard model really got to predict the existence of a new particle. And that was really exciting because it was the beginning of this journey where it started predicting a lot of particles. And but the problem is people looked for it and they couldn't see it. It certainly wasn't coming from space, at least not in any kind of number that we could detect. And it took particle accelerators to look for it. And then eventually people found this up quark, but it was way, way heavier. It was just like the up quark, but way heavier. And people were so delighted to see that they gave it also a really funny name, but it really helped. If you understand the history of why it showed up, you'll understand its name. And it was called the charm quark.
Yep.
It was called charm because it undid the strangeness of the strange, because it looked just like the up quark. And just like the up quark, it was much heavier. Just like the strange quark, it was much heavier than the up quark. Although it was even heavier. It was like heavier. And so that suddenly people said, like, there's this weird pattern that repeats. There's this up and down, and then there's charm and strange. And just the thing they have difference is that they're different particles, but they also weigh more, but they always weigh the same as each other. They just always seem to weigh more than the others. So that was the first time I realized there were more than just regular stuff around. There's stuff we can only make in certain circumstances. And in fact, even the fact that it came down from space is not because they're out in space. That's actually not why they're there. They rain down from space because they're very short-lived, and they're actually made when very energetic particles hit the upper atmosphere. And so they were only there just because they were being made by sort of a natural particle accelerator, which was cosmic radiation sometimes hits the atmosphere and it makes a very short-lived thing. And we kind of live in this particle accelerator on Earth because or particle collider on Earth, where stuff rains down, hits stuff, and makes showers of particles, and that's helped us discover a lot. And that's even happened until very recently too. I'll talk about that later because it's too complicated right now. So then we went on and made bigger and bigger particle accelerators because we're like, look, if we can make if we can take two things, collide them together, and then just get this jet of things coming out of it, new particles. That's one of the neat things about quantum mechanics is that you don't take like a watch and collide it and then get out like the springs and stuff. Like that's what happens classically is you get springs and gears and junk flies all over, you break it. Quantum mechanics is very different, where when you collide two things, you actually make brand new things. It's like two beach balls fly out. So you take two watches and then two beach balls fly out. And it's so that's one of the nice things about why particle accelerators and colliders are so important to physicists, because it allows us to just create particles and we get to see them until they decay away, and they usually last for a very short amount of time. So we try and smash them harder and harder together and see what we can get out. So when people started doing that in the 70s, because we already knew that the charm and strange existed, we got to, instead of waiting for them to come from space, we got to make them in a lab. And then we got to make the next type of particles. We made something called the bottom quark. And now bottom had a much more boring name because it was just trying to mimic the fact that it was yet again a even heavier down quark thing. It looked a lot like a down quark. That's why it's called bottom. But this time people were ready. They were ready. Physicists were ready because they said, well, look, we had the strange and then we fixed it when we ran to charm. But this time they said, look, this isn't weird. There's just a top quark out there. There's a top quark.
Yeah.
And we're like, look, there has to be, because there's these 5 quarks, and we're like, this is the missing piece. So unfortunately, though, it took a really, really big accelerator to build this, a really big one. It took a lot of time. And before The last particle that I'll get to later that was discovered, the search for top quark was really, really big because people were positive it was there. Everyone knew it was there. It just had to be because we literally I would tear my hair out if it turned out it didn't exist. And it
Right.
did. We eventually found it. It was very, very, very heavy, like
Nice.
way heavier than normal. It's actually it's like hundreds of times heavier. It's about 150 times heavier than a proton. So, but when we discovered it, it was great because it said, okay, this is almost there. Except there was still this unknown thing that was causing particles to have mass. And that was proposed by a guy named Peter Higgs, actually a really long time ago, long before this other stuff was discovered. But it was a really good theory, and that predicted this thing called the Higgs boson, which is unlike all the other particles. It's not a fermion; it's a boson, which is why it's called the Higgs boson. They even put it in the name for that reason because it's the one good counterexample to this sort of everyday mass particles, like all quarks and stuff, and electrons having mass. So then that was discovered really recently, like I don't remember what year.
2016? 2016?
Yeah, yeah, something like that. Yeah, very
Yeah.
recent. Yeah, less like 10 years for sure. So that completed what was called it completed the standard model in that it completed like what this arrangement of the standard model was. Although I just realized I forgot all the bosons that we mentioned earlier, so I should probably cover
No
those.
worries. It's hard. Honestly, if we went through every single particle in the standard model, we would probably be here for a little while trying to explain it.
Yes. What's funny is there's a thing called the particle zoo, which actually doesn't even refer to the standard model, which definitely is a zoo of particles. The particle zoo is a thing physicists started to call it back in the 60s and 70s when they started making things in particle colliders because you don't make the quarks by themselves. That was part of the mystery. The quarks are, like I mentioned, kaons. There's this whole other collage of particles that are almost like every combination of quark.
Oh yeah.
Like almost they always combine in either three or a pair and an antipair. And so if you just take the combinatorics of that, that's a lot. You can take an up, you can take a charm and a down. You can take three ups. You can take a up and a bottom. You can take a charm. Every single one, and there's an enormous collage of them, and they make those in particle colliders, and new ones are even being found today. The difference is now when we find a new one, it gets like maybe a little bit of news, but no one says like, we found a new thing, because it's actually, we don't even really see it as a new thing. It's almost just like finding a new kind of element or an isotope or something. So it doesn't get a lot of attention. We'll be like, oh, we found this one weird state, if let's say it's particularly rare or something, like two tops and a down quark or something, actually I don't even know which are the ones that still haven't been found, but there'll be really weird states that they'll eventually find them at the LHC, the Large Hadron Collider, but they're not big news stories because they're not new physics. They're new particles, but they're not new physics. We're not seeing anything new in their existence.
Isn't the pairing of these quarks in different arrangements, aren't they referred to as mesons?
So there's, just to add in lots of names for no good reasons, there are mesons, and then there's baryons. That's yet another subdivision of the standard model world. So and they have special names. So a meson is always just to get even weirder, a meson is always a boson, and a baryon, which is the other type of subdivision of the standard model, is always a fermion. And what a meson is always a quark and an anti-quark. And so for reasons we don't understand, we'll talk about this again. This is also one of the unsolved problems, but for reasons we don't understand, quark number always has to come in plus 3 quarks, or it has to equal 0 quarks. So a meson is a quark and an anti-quark. So its sum of total quark number is always 0. And we don't totally understand why. That particular mystery has actually been a huge part of my personal research. That's like one of the things that the stuff that I study having to do with neutrons is related to that. We're trying to figure out why this this number always seems to have to either come in 3 or 0, and there is no good explanation of it. So baryon is that's also, even though it's a weird name and stuff, it's actually one of the most important facts about the universe is that baryon number seems to look like it can't be changed, and we don't know if that's a rule, like it's a conservation rule, like conservation of energy. Is it that fundamental, or is it just a thing we happen to have never seen change? And it's really, that's one of the probably, I think that's one of the biggest mysteries of the universe at the moment. In particular, what's really weird about it is that baryons, this pair of 3 quarks, so one, it always has to be an up, or down, or top, it doesn't matter what they are, what quarks they are. There have to be 3 of them, and not an anti-quark of one of them. One of the biggest mysteries is why there's always more baryons than there are anti-baryons and in the universe. And the reason this is a mystery is because the universe has more baryons than antibaryons. The Big Bang did not produce an equal amount of baryons and antibaryons. Otherwise, everything would have annihilated, and we would just be a soup of energy. And
we wouldn't be here. Yeah,
we wouldn't be here. So this is yet one of those things. The Standard Model has all these great answers, and it just doesn't have an answer for that. It just says, "Look, there's more baryons. All right, deal with it."
That's fair.
And any experiment we do in a lab to date doesn't show a difference enough to explain why one would be preferred and the other one's not preferred.
Interesting. Another thing that since we're kind of talking about the problems now, I guess we might as well transition a little bit.
Well, you brought up mesons and baryons. So.
That was my fault. It's already, this particle physics is already extremely complicated at its most basic form, and then whenever you start getting into the weeds, it's like, oh my, okay, let's take a step back really quick.
What you mentioned though, this baryon thing, I'm glad it came up though, because that's the name of this episode. It's the first example of an asymmetry that exists in nature, and that's what's really interesting about it. It's an asymmetry between matter and antimatter. And in particular, it's an asymmetry that we don't understand because we can't find it in other ways when we look for it.
Absolutely. Yeah, we're gonna talk about that in segment 2. So before we conclude the first segment, I kind of want to highlight what all like in a list, what are the problems with the Standard Model, or not problems, but what is the Standard Model not able to answer at the moment. And one thing you said is gravity. The other one that I think, unless you want to go into that more, because it was more prefaced. I know there are efforts to try to find a fundamental force carrier for gravity because of the evidence that we have with what we found at LIGO not that long ago with discovering gravitational waves. So if you want to dive into that a little bit more.
Sure. So gravity definitely does a lot of things that are similar to everything in the Standard Model. It seems to transmit at the speed of light, like all massless carrier particles. I actually forgot to name them all, but there's photons that carries light. That one discovered a long time ago. I mean, we realized that we literally see it every day. So our bodies are designed to see light. So that one was really helpful, or really easy to discover. Then there's also there's something called the W boson. Very not normal, but that's involved in nuclear decay. So it wasn't discovered until the modern era when we started discovering how neutrons and protons interacted. Then there's another particle that has no mass but is very, very strong, and that's called the gluon. And that one's so tiny, or that one's so strong that it only occurs inside of a nucleus. And again, it wasn't discovered until we discovered nuclear physics, because until we actually started probing atoms, we had no idea that this was even going on inside of us all of the time. What's really hilarious is that even though I love this fact about the gluon, even though the gluon is massless, most of our mass comes from gluons. You are personally mostly made of gluons. And that is a very weird thing, because everyone says, well, I don't even know what that is, and it doesn't matter. But most of your mass comes from a gluon, not from quarks, not from electrons. Gluons there are so many of them that Einstein's theory of special relativity, not general relativity, says that even massless things that are contained inside of a little box will still have mass. That's the E equals mc squared part of
Right.
Einstein's theory. So, and we discovered this only recently, but we're mostly made of gluons. I know Carl Sagan liked to say we were made of stardust. Well, the stardust that we were made of was also gluons. So, and then there's these other two that really are unusual called W and Z bosons. And those really just have to do with radioactivity. So
Right.
they get a lot of press, even though those particles themselves don't. But like, so for example, when things decay radioactively, it's usually because of something called the W and Z boson. They're causing that decay. And then I think that's out. Oh, but you want to hear about what? Can I go into gravity now? Is that
Sure. Yeah,
yeah?
absolutely.
Okay.
Why not?
So people tried to use this to, like, early on. Like I said, it went all the way back to Einstein. He went to his deathbed trying to figure this out. But as we learned more about it, we knew at least how the math of gravity worked and how that would guide if there was a quantum gravity, a
Mhm.
quantum theory of gravity. And so one of the things we knew is we knew that gravity had to transmit information the way, like you said, gravity waves were transmitted. And even though we only recently discovered gravity waves, in fact, my relativity professor, Kip Thorne, won the Nobel Prize for working on that. I remember when I was taking class from him, he said, 20 years from now, I'm gonna, we're gonna try and discover gravity waves, gravitational waves. And I was lucky enough to actually be hanging out with him the day that he found out that had happened. I was
Wow.
really, I actually was interviewing for my own podcast. And it was really cool. And he said he couldn't tell us what it was, but he's like, we opened the box and it was really interesting. That's all he could tell us. And then I only found out later why he was so excited about what they had found in the box, and that was because they had discovered gravitational waves, and he won the Nobel Prize for that. But gravitational waves are not quantum mechanics; they are classical. So they can be explained classically, but they have certain properties that make them have certain mathematical structure to them, which has to do with their symmetries. And again, related to the topic of this podcast, asymmetries, the thing I study, fundamental symmetries. That's the field I study. So gravity waves have like a different structure than photons. Photons are bosons. They have spin one.
Hmm.
Again, a weird thing that only really kind of makes sense in quantum mechanics. But graviton, if there was a particle that carried gravity, it would have to be something like a fundamental gravity wave, like a thing just like light. It can be explained by photons. There'd be something
Hmm.
that where gravity waves could be explained by gravitons. That's the name they gave it. Even though the graviton's never been discovered, it has a name because we like to name things. So a graviton would be a little different in that it'd have spin two, and it'd have to, because of the way it stretches and warps space. It would have to be a spin two object, sometimes called a tensor object. Tensor, just because that's the type of mathematical object that explains gravity. So
Hmm.
he would have to transmit that. Otherwise, he wouldn't be able to tell two things at a distance what gravity was doing. So we know that even if we could figure out how to make quantum mechanics work with gravity, it would have to have this particle. This particle would be really weak. That's one of the reasons why we can't find it in an accelerator. It'd be way
Right.
weaker than a photon, meaning that when I say weak, I mean its chance of interacting with a particle that has mass is way lower than the chance a photon does interacting with a particle that has charge.
Sorry, even like lower than the chance that like a neutrino would even interact with something that with mass. Is that true?
Yes, that absolutely. In fact, that neutrinos interact via something called the weak force. And it's called the weak force because it's much weaker than the strong force, and it's weaker than the
Electromagnetism.
electromagnetism. But
Hmm.
although even that comes with a weird mathematical caveat, so I won't go into that. It's too complicated. It actually isn't weaker than electromagnetism, but in practice, okay. Like, let's not go there. The point is, gravity is way weaker than all of those. So gravity doesn't even come on the scale. And so the
Yep.
odds that we would, for example, I said we in particle accelerators we can smash stuff together and get things out. We would have to smash together so many things and with so much energy to ever even see a single graviton do anything interesting that we're just never going to see that in a collider. And so this creates a fundamental problem, which is not just that we don't know how to mathematically unify gravity with quantum mechanics, we can't experimentally make it. And this is and that causes us to not really be able to see the two colliding, literally colliding in real life. And this makes all sorts of issues where we don't understand what happens in parts of the universe. We don't happen like really, really briefly at the beginning of the Big Bang. Models break down there. We don't know what happens inside a black hole. We don't know what happens inside or near the singularity of a black hole. There's all these places where quantum mechanics and gravity should unify in some way. We know they have to unify because they're kind of on a collision course. It's like watching two trains come together, but we don't have any evidence of what will actually happen. This was actually really well demonstrated in the movie Interstellar, which was also made by Kip Thorne.
Yep.
So the same guy. And it's a really good movie. And I was really happy to see the new Thor. Natalie Portman's character, who I actually helped develop her character, not her character, but like her set in the original Thor. But I really liked, she said, she's trying to explain complicated stuff related to traveling through space and time, and she says, watch Interstellar, it'll explain it better. And that's really true. Interstellar has a lot of really deep points in it, and they might sound like just science fiction fluff, but there are really good points. So one of the things that happens is Interstellar, they say, look, we can't, the character he's kind of a caricature of what Kip Thorne's like in real life. He's a physicist, he's trying to explain quantum gravity, and he can't. And he says, look, we can't even see inside a black hole, so we can't see this. It's literally like excluded from our view. And that's very much what it's like, unfortunately.
Yeah, wasn't there a robot named Kip in the movie? I'm pretty sure
there was, the one that blows up. I'm not sure why, but they named one after him.
That's beautiful. I didn't know that until way after the fact. And I'm like, that's a really cool like little movie detail. I like that.
Yeah.
I like that a lot. That's cool. So one other thing I think before we run out of here for the segment is dark matter particles, right? We also can't roll the dice with dark matter particles with the standard model.
That is another example of something the standard model does not explain. When we look at the way the universe expands, and also probably more importantly, the way galaxies rotate, we can tell that there's and then finally we can look at the way galaxies warp galaxies behind them through almost like a gravitational lens type of thing. It is really clear to us that there's this very large chunk of matter out there that we can't see at all. And when I say we can't see, I mean it doesn't interact with light. It doesn't seem to clump together the way planets do. It does not seem to be made up of little black holes. That's actually been studied pretty well. Because gravity, you can't see black holes, but that was an early explanation. That was called the macho explanation. It had a funny name, macho.
Love that.
Instead, what seemed to really win out was something called the WIMP. So there used to be a WIMP and macho battle, but machos were pretty much ruled out. I'm sure there's somebody who will disagree with me, but for the most part, the consensus is that those are ruled out. And WIMPs, that was just what WIMPs were like little tiny heavy particles out there that don't interact with anything. And neutrinos cannot be WIMPs. That's not good enough. They have to be heavier than that. A WIMP stands for weakly interacting massive particle. That means a particle that interacts via the weak force, but or any weak force. It doesn't have to be the weak force, but if it interacts through something that's very weak, and that it has lots of mass, but it just flies around. And what's possible is that dark matter is just stuff flying through us right now. Like this room might actually be full of dark matter at the moment, and we don't realize it. And we can only see it because we see gravity behaving at large scales as if there's this stuff flying around. But there's nothing that we can make in a collider. There's nothing in the standard model that says what it can be. So we just can't find it, and that got even more frustrating recently because after we discovered the Higgs, we thought, we're going to finally find what this dark matter is. We thought it was going to be this pattern of, you remember at the beginning of the show, I said that, we found the strange, and then, yay, we found the charm. And then we found the bottom, yay, we found the top. and then we look for the Higgs. There it is. We were hoping that was going to happen with dark matter. We thought there was going to be this thing. Oh, there it is. It's this 300 GeV thing. Thank goodness. But the LHC has not found anything. It has just found this desert of particles. And so that trend of finding new stuff ended, and it was very frustrating. And it's frustrating for a lot of reasons, not just because we don't have an explanation, but also like it says, well, what are we supposed to do? Build a bigger collider? Well, how much bigger is it? Is it 10 times bigger? Are we going to build one the entire diameter of the Earth? Are we going to build one the diameter of the, are we going to build one the size of the solar system? We don't know. Why would we? What do we do? Because there's no theory that says what is the next thing. We ended this trend of finding like a little hint. We just know something's there. We just don't know what it is. So we're trying to figure out other ways to look for this dark matter particle. Maybe it's not even a particle. I don't know.
That's the cool thing about it. I think. Yeah.
We know it's there because it's most of everything. But what is it?
Yeah, I guess something cute to really end this segment right here by just saying, we've spent the majority of this segment talking about things that are visible to us. It's the visible matter, and then dark matter and dark energy accounts for literally the majority of the universe. Like what 5% is the visible matter that we spent all this time talking about. Gotta love it. All right, so whenever we come back, we're gonna actually talk more about the asymmetries of the universe. So stick around. All right, we're back. This is segment 2, and we're now getting into the asymmetries. We've done a lot of we've laid groundwork. We've talked about the standard model. We've briefly touched on the asymmetries, but now we're going to go into depth more. We mentioned this in segment 1. I'll bring it back up again. It's about the matter-antimatter imbalance. And before we get into this, I kind of want to throw a little historical fact about antimatter. And Paul Dirac, in I think 1928, was the first person to posit the existence of positrons, or the antimatter particle of the electron. And he did that with the Dirac equation, and it turned out to be true, which is really cool. I wanted to throw it out there, but I want to take this through like a 3-step approach. What is happening? How do we know that there is an imbalance? And then what are we finding? Like how are we trying to solve this mystery? Because it is a big mystery. It's the reason why you and I are literally here having this conversation. So talk to me. What is this imbalance? Why does it occur?
Okay. Well, I want to briefly talk about. You mentioned the Dirac equation, so I want to tell you a little bit about that. So just like I mentioned earlier, there's an up and down chord. People are like, well, there's a bottom, so there's got to be a charm, or there should be a top. The Dirac equation was really similar to that, and then while it's a little bit more complicated than like the square root of 1 equal, it like this taking the square root of something. The square root of x equals 1 has 2 solutions. It has +1 and it has -1. The Dirac equation was a lot like that. That's part of what led people to think there must be antimatter. Led him to think there's antimatter. His equation just had 2 states. It had a plus state and a minus state. And I was like, what is this minus state? Why does that solve the equation? And this was a really frustrating moment, but also really exciting because it was a good time when people said, well, just because it's a math thing doesn't mean it's real. Because we do, electrons were always one charge and never the other charge. We're like, Dirac, like, calm down. Your equation just is it's overly fancy or something. This is the first time that theoretical physics really, I think, predicted something really tangible. Like, it was like, no, there's this other electron and it has the opposite charge of an electron, even though we never see it in real life. So it was related to the asymmetry. We were like, if it's real, then where is it? And people were like, well, it doesn't exist at all. So that was the main idea. It was like, just the universe doesn't have it, deal with it. But it turns out the universe does have it. So it didn't. That was the first time we realized, wait a minute, why is the universe made of electrons? Why do we only see electrons in the lab? And yet we can make a positron. And I was really fortunate to learn physics in the very building that the positron was discovered. auditorium or Bridge Hall at Caltech is there's a little plaque on there that says this is where the positron was discovered. And what was
Nice.
great is as I went to lab, there was a little bubble chamber outside that somebody was keeping set up for students to see as they walked in, and you could see positrons every day in it. They're just every day positrons would show up. So I love that in the building that the positron was first found, positrons are happening all the time. You're literally in a room. These antimatter versions of electrons are in the room with you right now. There's just way less of them than there are electrons.
It's
We
awesome.
don't realize they're there. I mean, they had to be discovered first, but they're there. And yeah, so this led to the discovery that this could happen. But also, when we made them in the lab, they were always 50-50. If you have enough energy to make an electron, you also have the mass of 2 electrons. You automatically can make 2 at once. They'll just split apart. You'll see no difference between them. They just both pop into existence. You'll see an electron and an anti-electron will just fly out of things sometimes. And that was really strange because that's not what we see in the world. We see only electrons. That's like why is it in one case we only see electrons, and then but if we have enough energy, we go over a certain energy, we make both. And this was the first time that this asymmetry of matter and antimatter really came to our attention, because we were seeing it in one case where there was no asymmetry, and then we were seeing the universe where there was this enormous asymmetry.
The antimatter name is both beautiful and like very sci-fi at the same time. You know what I mean? Like they get antimatter. People are like, well, antimatter it's just not real. No, it's very real. It's just explaining that like it's matter. It is matter. Like the anti doesn't mean that it's not matter. It's definitely matter. And it just has opposite properties of what matter particles have. Yeah. It's a little I shouldn't say it's sci-fi, it's just misleading, I guess.
Yeah. Well, it's used in sci-fi, so that's part of it. But but also, I mean, it has some other very weird things about it. Like Richard Feynman described it a lot as like matter going backward in time. And some people don't like hearing that for description of it. That is very close to what it behaves like. And that relates. I like that description because it relates to another asymmetry that we don't understand, which is the asymmetry of time versus going backward in time. And that one's a very different one from the rest of the asymmetries, because that one at the moment we know there's a symmetry of time that has to do with our understanding of the past and what will happen in the future, and it has to do with entropy, because entropy increases, which again is related to our understanding of the past. So that one gets also very confusing, because that one, it's not clear we measure time accurately in a lab anyway. So because we experience time. That's one of the things that makes it very different. And yet, when you take the laws of physics, you can treat time just like any other thing. You can treat it like the X dimension or the Y dimension or charge. So you can do things like say, well, what if we put a negative time sign in there? What do we get? And that's one of the weird things, is that you kind of get the properties of antimatter. So so we introduced that as we have a term for it in the fundamental symmetries world. We just call it the letter T. It's not shocking, but so there's various symmetries that we have that we refer to them. So there's charge, there's parity, there's time. Parity is like, CPT. And that's what we go after. We go after like, well, what if we do this experiment and we play it backward in time? Well, we get the same thing. And so we'll try and set up the experiment to be backward in time and see, well, then do nothing but antiparticles come out in that case? And then we're always looking for some little difference between changing it backward in time or changing it through parity, meaning doing it like it's left-handed versus right-handed, as if the experiment was done in a mirror. And changing the charge. So that's in the case of, like I said, an electron has a positive charge and electron has a negative charge, and a positron has positive charge. So that's how we do experiments where we flip those and see what happens. And we're trying to find any kind of imbalance.
It's amazing. So how do we know how much matter versus antimatter there was? Why is there a certain amount of matter existing, but yet everything else, was annihilated at some point?
Yeah, that's a great question. So we don't actually directly know that there's matter versus antimatter. What we really measure today is how much matter versus energy is there, because we don't see antimatter. Like when we go into the sky, and this comes up a lot where people think, well, maybe maybe that's an anti-galaxy or something. And there's actually a lot of reasons why we're pretty sure that it's not like galaxy, anti-galaxy, galaxy, anti. That would be one way that we would have maybe the two just clumped together differently. We're pretty sure that that is not the case, and there's a lot of reasons for that. But what we do see is we see the amount of light versus matter, and the reason that matters is because and sometimes that's called the
I know we measure.
Anyway, we can measure that.
No
We can measure that ratio, and it's very big. There's way more light than matter, so it implied that at the beginning of the universe there was a lot of antimatter, but antimatter annihilates to create energy. So that's what we see. Is we just see that there's this afterglow of the
CMB.
Yeah, that's right. The cosmic microwave background. Yeah.
Yep.
I didn't know you got to abbreviate it on this show. That's cool.
Yeah, sorry, cosmic microwave background, CMB.
Yeah, so we see that, and by measuring the properties of that really carefully, how much splotchiness there is in it, we can tell. We can measure that value very carefully. The ratio of baryons to photons.
What is that? One in every. Was it 100 billion or just one in every a billion? I forget what the exact number is.
I don't have the number. I should have it memorized because I've written code to use that number and make predictions. But I think it's roughly 10 to the 10. So yeah, it'd be 10 billion.
Okay.
There's some number. Physicists don't care about the things in front. We only care about the exponents.
That's fair. That's fair.
So basically, like that means that the asymmetry we're looking for between matter and antimatter is not big. We're looking for one that's just, like you said, one in every 10 billion-ish, kind of that scale. But we don't see that even close in a lab. We don't see anything remotely close to that big in a lab. And it's funny because I said that's small, because it's like, well, 1 in 10 billion, that's tiny. But remember, the standard model has up to 40 decimal places sometimes. So 1 in 10 billion that's huge when you're talking about 40 decimal places.
That's a great way to put that.
And we're just not seeing it. And that's what's frustrating. We're trying to find, like, well, at least find that. We can't. It also shows how hard looking for these asymmetries can be, because we're not looking for a giant whopping asymmetry. We're not, looking for like a raised eyebrow kind of thing. We're looking for a thing that if you saw it on a human face or something, you would think you were just looking at an exact flipped image or something like that. And we don't see that.
Dang. So what are we doing to try to figure out how this asymmetry arose? Like for me, I've been doing my own research, but I've heard of like the TK2 or T2K experiment. Are you familiar with that?
I'm embarrassed to say that I'm familiar with it, but I don't know enough about it to talk about it.
All I know is maybe you can.
If I know it, I would have looked it up before.
No, don't worry.
Definitely should know, but there's a lot of colleagues who would be mad at me for not knowing that.
Well, it has to do with and maybe I'll just jog your memory. It's based on neutrino oscillations. So they're looking at neutrino versus antineutrino oscillations, and essentially that's just like the change of the lepton number between what it would be as an electron neutrino and a muon neutrino changing it.
So there are experiments that look for lepton number changing, but that's not an example of that. So when a neutrino turns from an electron to an electron neutrino to a muon neutrino. By the way, when I was trying to give all the particles of the standard model, I didn't even get to the neutrinos.
I was going to say something, but it's no big deal.
Yeah, but I'll just cover them right now. So neutrinos are yet another part of the standard model, where just like they are kind of like sort of a weird copy of down quarks, except unlike down quarks, there's these heavy versions of leptons, and they have charge, and then there's this chargeless version that have very little mass, except they don't have zero mass. They just have very little mass, really, really, really little mass. Again, one of the weird things, like why is it zero? It should be zero, but it's not, or maybe it shouldn't. But then on top of that, just like there's three flavors of quarks, there's the up and down flavor, there's the charm strange flavor, and there's the top bottom flavor. There's also three flavors of of leptons. So there's the electron and the electron neutrino, there's the muon and the muon neutrino, and there's the tau quark and the tau neutrino. In fact, the fact that it's called tau is actually, that's like an homage to the top quark, by the way. That's not a coincidence. Because they for some reason we think that's a pattern, and we don't know what that pattern is. We don't understand why are there three of these? Why are there three of those?
Yeah.
It just seems to work, and the math matches up. It's very weird.
The math is mathing.
Yeah, it just happens. And lots of stuff in this air ball happens in threes, by the way. Also not completely clear why. So when one of the things that neutrinos can do is they can change from one flavor to the other. Quarks can't do that. I mean, they could in theory, but they don't, because they're so different from it. They're so massively different from each other, literally massive. They don't flip. But neutrinos are so light, they can just sort of casually change from one into the other.
That's what I meant to say. I'm sorry. I said lepton number. I meant to say lepton flavor.
Yes,
apologies.
Flavor. Yep, okay. Yeah, we like to, no problem, because we like to throw weird names and stuff like that. Yeah, we call it flavor like it's an ice cream for some reason. And that's what those three generations are called, flavors. Again, there's no explanation of why those flavors exist. Why are there three? What causes them to be that way? Why do they weigh different amounts? We don't know. It's absolutely not known what that is. There's no theory that explains that. It's not an asymmetry. Well, I guess it's a kind of asymmetry, but it's an open problem. So if anybody listening wants to try and solve it, please do. That's hard. One of the places that you can look for these asymmetries is when things change flavor, or they switch between up and down, or top and bottom, or electron to, and that's because those are all governed by something called the weak force, and the weak force is one place we're trying to find these asymmetries between matter and antimatter. In fact, actually, the first asymmetry, like really interesting asymmetry, was discovered not in the electromagnetic force, it was discovered in the weak force, because that was the first time we could do an experiment, and we discovered that if you do the experiment in a mirror, you get a different result. And neutrinos played a role in that, because neutrinos are always left-handed when they come out, and that was when I say left-handed, I mean, it's weird because it's not like a hand, but if this is a rule you use a lot in physics, is you use your thumb. This is my right hand, sorry, but here's my left hand. You use your thumb that points to the direction something's traveling, and then my fingers point to the direction it's spinning. Neutrinos always come out like that, and they don't come out. The reverse in a mirror doesn't happen, and so that changes the way an experiment happens. And so there's lots of experiments you can do where you can just look at it in a mirror, and you'll be able to tell whether it was done for real or it was a photo flipped after the fact. And that was the first time we said, wait a minute, but I thought space was symmetric. It's like, nope, space is not always symmetric in certain cases. That's where parity was introduced. That's why we call it parity, because that's left-handed versus right-handed. So
I see. The T2K experiment was based on neutrino oscillation between a muon and electron neutrinos, and then what they found is that it happened more often than what you would see through anti-neutrino oscillations. So that was where the asymmetry lied. However, I will state that it's not something that is a true discovery yet, because it's not something that is 5 sigma. It's they classified it as a 3 sigma. So it's not a true.
I hadn't heard of it. No, I should have heard of it. If I was more up to date, I would have. But yeah, so that's one of the things that is tricky about this stuff, working with asymmetries and just particle physics in general, is that a lot of times stuff is very tantalizing. We see results like that, and we're like, oh, is this it? Finally, please. And then sometimes we go and we do it more. The only way to get around the statistical stuff is you just do it 1,000 times more, and which is the scientific method. That's how you're supposed to do it. And then and then sometimes it turns into a discovery. Then other times it just goes, oh well.
Yep. Yeah. So it was just a promising thing, right? It's not actually a true discovery.
Another way my advisor is working on, lots of people are working on an experiment using, I think we're going to get into this in the next segment, like the specific parts of the research that I use, but you can look for it in neutrons themselves. Regular neutrons are a place that people are looking for CP violation, meaning charge and parity violation, that might explain the matter-antimatter asymmetry of the universe. And that's in the case that you can look for things that shouldn't exist but might exist, or they might be bigger than they're supposed to. So a really good example of that is the electric dipole moment of a neutron. So neutrons have a magnetic dipole moment. That part's not new. So you can put them in magnetic field, and they'll align or anti-align with the magnetic field, but they shouldn't really have they shouldn't have an electric dipole moment except incredibly tiny. And so far, people trying to measure it can't find it yet because it's so tiny. But we're hoping that someday, if we find it and it's bigger than it's supposed to be, meaning it's bigger than the standard model would predict, then that could be a really good hint of some asymmetry that's occurring. So that's one of the reasons why we're doing that. So it's a great example of a weird experiment where you try to measure something really carefully, and then you're trying to see if this asymmetry will crop up.
Interesting. I think another asymmetry that you might be more familiar with is that there is a kaon asymmetry. Is that true?
Yes, that was the first time that any CP was found, and it's nice because it was also the first strange particle. That literally had strangeness. So it was the first one that behaved differently, not just on the asymmetry, but it was just oddly heavy compared to other things that we saw in real life, not in real life, but in everyday life. And one of the things they found is that kaons and anti-kaons don't quite behave the same. And that was the first time we said, "Hey, look, this isn't non-existent. This is real." And that gave us a lot of hope that there really was this light at the end of the asymmetry tunnel, that like matter and antimatter behave differently, but we couldn't. It wasn't enough. Unfortunately, it just wasn't enough. It's nowhere close to explain the Big Bang. So that made it so messy, because it's like, okay, so there's some, but not enough. It's just
Of course. That's I feel like it's just going to be a collective effort of it seems like there's a decent amount of asymmetries, and probably a lot to still be found that could even like accumulate to end up explaining the asymmetry overall of matter.
Yeah, it could also. It could easily happen just at an energy scale we haven't discovered yet. So
true, very true. Man, I think we covered that. I'm pretty sure. Is there any experiments that you're aware of that are continuing to look into this asymmetry, or like any specific ones that you know of?
The dipole moment experiments, I think, are the most promising at the moment, but there's others too. There's things related to looking at whether baryon number is conserved, for example. So that could relate to the asymmetry. So an experiment I'm particularly interested in is that sometimes neutrons, maybe they turn into anti-neutrons, and that would be a violation of baryon conservation, baryon number. So remember, I said at the very beginning, I said baryons means 3 quarks, and when we look at a big vat of water, and it's full of baryons, it's full of protons, which are a really great baryon. That's the most fundamental. It's the most common baryon in the universe by a lot. That's what most things are, is just a hydrogen atom.
Right.
Anyway, H2O, so lots of hydrogen atoms in a vat of water, and we can just sit there and we can just look for them turning into something else. We can see, do they fall apart from time to time? Meaning, do they go from one baryon to just nothing? From 3 quarks to 0 quarks, and we don't see that like at all. It doesn't mean it doesn't ever happen, but it lets us put really good limits on how infrequently it happens, and it's way longer than the lifetime of the universe, which is also good, because then the sun would be here and we're here, and if they weren't true, we'd fall apart. But that doesn't happen. But it's not necessarily clear that neutrons don't turn into anti-neutrons. That's still allowed. So that's a possibility. And so that's an experiment I'm particularly interested in, actually.
Interesting. Well, I think since we're going to talk about that in the next segment, let's conclude this one. So whenever we come back, we're going to be jumping into more of Kevin's experiments about ultra-cold neutrons. All right, this is the final segment of Asymmetries of the Universe. We've talked about a lot. I hope that you're still hanging in there.
I'm hanging in.
This is the knockout round, at least for this episode, and we're gonna continue talking about I guess more asymmetries, but more towards what Kevin does with his research. So, Kevin, do you want to start out by talking about ultracold neutrons, and then run through your research? It's literally your segment. I'm just gonna be here, layperson, asking the questions, or just going, "Oh wow, that's awesome."
Yeah,
So,
I'd love to.
take it away, man.
So, my advisor introduced me to when I went back to grad school. My advisor introduced me to ultracold neutrons. I hadn't even heard of them before that. Certainly knew what a neutron was, but
Mhm.
a really neat thing that we discovered. It was first Fermi proposed these for a long time ago. So, anyway, he was one of the people who proposed it. So, there was this really amazing realization that when you freeze something, when you get cold enough, because of quantum mechanics, something called the Heisenberg uncertainty principle causes its size to expand. This is because you can't know something's energy and its speed and its location at the same time. So if you know its energy really well, you know that it's cold, like very, very cold. That means you don't know quite where it's cold. Okay, this is really a really important property of something that gets cold. And so what happens is when neutrons do that, they spread out and they don't interact with one nucleus, they interact with many nuclei at once. And this is a really neat thing that only quantum mechanics allows you to do, where a thing that came from a nucleus could then suddenly be in like several hundred nuclei, sort of blurring over the thing. Anyway, so when you do that though, you can do really neat things with neutrons, because they suddenly stop behaving like little particles that came from a tiny nucleus. They start behaving more like a photon or a particle of light, because they behave like a blurry wave. And so you can do things like you can bounce them off of surfaces, collection of other nuclei. Um, Also, what's neat about neutrons in particular is there's a really neat trifecta that occurs where, just by random coincidence, the properties of a neutron at this temperature happen to be all around the scale that's very usable in a lab. And those three properties are, so one is it has, I mentioned earlier, a neutron has a magnetic moment, which means that you can align it or anti-align it with a magnetic field.
Mhm.
And the energy of that happens to be roughly the size of what you can trap in, a magnet you'd see in an MRI or something. Several tests. You can trap neutrons, and you can flip their spin, and you can align them or anti-align them. It also happens that an ultra cold neutron, when you get it cold enough, its its mass is such that it bounces roughly the height of a basketball.
What?
Like humans, it goes like a few meters in the air, and it will turn around from gravity and come back down. It acts like a very cold gas.
That's
so
really cool.
so these three things come together where you can trap them in bottles, because you bounce them off of surfaces. Normally neutrons just fly out of stuff, but you can trap them just like a regular bottle, and then you can manipulate their magnetic field, and you can manipulate their gravity. And so this is what makes them really, really good at testing all kinds of stuff, including some parts of gravity. You can't quite test quantum gravity, but you can test stuff about gravity related to this, because you could actually see the neutron interacting with gravity. So you know that, like, for example, we know neutrons do interact with gravity because we see them go up and fall back down. So, let's say someone had a theory that said, well, gravity was only among protons. Like, only protons participate. We know that's not true. Neutrons also participate in gravity. The other thing that's really nice about neutrons that makes them so useful for testing fundamental symmetries of nature, particularly ultracold neutrons, the neutron itself also participates in every single force that we mentioned in the Standard Model. So we know that they participate in gravity. That's not out in the Standard Model, but we also know they participate in the weak force, the strong force, and the electromagnetic force. And so we get to study every little piece of those interacting with each other, which means we get to see, we get to do all these little tricks, like maybe if we flip this, then that will happen, and if we flip this one, then that will happen. We get to probe almost every single part of the Standard Model. So ultracold neutrons really behave a lot like a tiny little particle collider, and we can just do lots of great things with them. So some examples are when I first started working with ultracold neutrons, I joined a group that was already studying something called beta asymmetry. And beta decay asymmetry is just a thing that was discovered about nuclear physics, that where if you align the spin of a neutron one way, you get a different decay result than if you align it the other way. And we don't quite know why this happens. It's just it is hard coded into the standard model. It's a thing and it exists. And it's just a way that nature chose to say, like, well, if you're aligning a magnet this way, then some things will go off more that way than they will the other way. And we measured it. And because the ultracold neutrons were so useful, we measured it better than it had ever been measured before, using any other kind of nuclear decay.
Interesting.
And that was just because we could hold them in a trap by themselves, and we can measure the most fundamental property and not worry about anything else interacting with them. Then, like for my thesis, we talked about gravitons being tensor particles. Do you remember that? We said that there might be these spin 2 particles. So for my thesis, I also looked at the decay of ultracold neutrons, and I was trying to see if there's any evidence that tensor particles existed at all. And I don't mean I was looking for a graviton, I was looking for any tensor particle. And this was important because we also talked about dark matter. If there were tensor particles, that would be a potential candidate for dark matter. There would be these hidden tensor particles that have mass and fly around and do stuff. I didn't find any tensor particles. That's okay. It was a thesis, not a Nobel Prize. So didn't expect to find. That's all right. That's how most research goes. So
still useful.
Then, and then I told you about there's another really exciting experiment looking for the electron dipole moment, or the electric dipole moment of the neutron. That's a very hard experiment to do, and it's taking a long time. So it's not done yet. But and I'm not even working on that one, but it's still interesting. And then another experiment I am working on that was also really exciting, and we're still continuing to do better at it, is looking for just the lifetime of the neutron. So a neutron is not stable once it leaves the nucleus. Neutrons decay into protons. They don't stay around as neutrons. So that amount of time, the average amount of time that a neutron stays a neutron then turns into a proton, is called the neutron lifetime. And it's about 15 minutes. And the reason this is hard to measure normally is because normally neutrons fly out of the experimental hall way before 15 minutes. They're usually out of the experimental hall. If you make a neutron, like let's say from an atom bomb or from a nuclear reactor, they're there for like a fraction of a second, and they either very quickly combine back into some other nucleus, or they fly off into nowhere. And they leave the room because they're not normally trapped. So they either fly out or they travel a short amount of distance and then recapture into a nucleus. But using ultracold neutrons, we can keep free neutrons, free from a nucleus. We can trap them in empty space for a really long time, and that amount of time is like if they didn't decay, we could trap them for like a week. Like a week.
That's awesome.
That's how good our traps are. So we're working on this experiment we did called the UCN Tau experiment. It uses a special kind of magnets called Hallbach array magnets, and they're arranged in a pattern where the neutron never touches anything. It just bounces off the magnetic field, and then it uses gravity on the other side, and it literally it's like a little we call it the bathtub, and the neutrons just bounce around inside this thing, and they never touch anything. So whenever they leave, it means they turned into something. They either turned into a proton or they turned into something else. And I say that we turned into something else because what's even more interesting is that when we measured this value, so we measured the best neutron lifetime that anyone had ever measured, down to 0.3 seconds. So we're working on even better now. We're taking data on even more accurate. But what was really exciting about this is that it didn't agree with the neutron lifetime when people used a different method to measure it. That is, when they looked for just the proton coming out, which is what a neutron is supposed to turn into, they get a different number. And the two numbers don't agree with each other.
Really?
By a lot. Yes, by several seconds. And so this got immediately this caused a bunch of theorists to get really excited. So you got to be careful when you mention things, theorists. In particular, we mentioned one of our favorite terms that we said earlier. One person said, "Hey, well, what if they're turning into dark matter, and that's why you're not seeing it. And the second you put dark matter into the abstract of a vapor, there's going to be like 20 more papers about it afterwards, because as we mentioned at the very beginning, dark matter is a huge mystery, and people are trying to find that. And so this was very exciting. People are like, well, maybe this is an explanation of what dark matter is. Now, there's a lot of reasons that probably isn't what's happening, but it's still really exciting. So that's also why we're continuing that experiment. We're trying to see maybe even neutrons just turn into dark matter. Maybe they help explain. So I also talked about how sometimes experiments you can see if a neutron turns into an anti-neutron, or maybe it turns into some other particle. That's why I like using neutrons.
That's awesome. That's awesome. Just briefly offset, we talked about the new Oppenheimer movie. I know you said that you wanted to mention something about that. So
yeah, and I forgot to bring that. All right. Yeah. So ultracold. So all the research I do is with ultracold neutrons at the world's brightest ultracold neutron source. And it wasn't when I started. We worked. A lot of us put in a lot of effort to make that source better and better and better. And it's much brighter now. And by bright, I mean just the number of ultracold neutrons it makes. And now it's the world's brightest ultracold neutron source. And that's all in Los Alamos, New Mexico. And that's done on LANCE. And LANCE is a proton accelerator beam at Los Alamos. And Los Alamos was picked by Robert Oppenheimer during the middle of World War II as to be the secret base that the U.S. would develop the first nuclear bomb. And that was very much related to neutrons, because a nuclear bomb is not just about uranium or plutonium. Those words are, I mean, those elements are important. They play a role, but really what's key to a nuclear bomb is that it's a device that suddenly makes a lot of neutrons at once. It makes several grams of neutrons in a millionth of a second. And that is what actually is what is going on when a atom bomb goes off, is that a whole bunch of neutrons are made very, very quickly, and they, in a chain reaction, one neutron goes to the other one, releases two more. And the fact that you just exponentially increase the number of neutrons you make is what causes the bomb to release so much energy at once. That's also what makes nuclear power work, except there it's not all at once, thank goodness. In fact, it's designed so that can't happen. Some people think that power plants can explode like a bomb. They definitely cannot. They never will ever be able to get to that point, but they can release a lot of energy at once, and you can use that energy. Anyway, the reason this has to do with Oppenheimer is that Oppenheimer, the movie coming out, we mentioned Interstellar. Oppenheimer is actually made by Christopher Nolan. He's just a fantastic director. I think he's great. And I think it's going to be one of the best movies. I'm so excited about it. But it's about Robert Oppenheimer and his quest, both, his moral quest, because he had to deal with the fact that he made this like this terrible weapon, but also just like that he had to unleash this power. And guess what? We didn't pick this, that this power can be released. Humans didn't pick that. Nature picked that. Somebody picked it. Something or something. Or I'll leave that up to you to decide. But he just was just like all of us who study this. We just study it. We just learn that it's there. That we don't pick.
Exactly.
I didn't get to snap my fingers and decide that nuclear power existed or not. It exists whether I want it to or not. And we get to pick what we do with it. Anyway, Oppenheimer picked Los Alamos because he went there as a kid, and it's a really amazing place. It's actually the first inhabited place in what's now the legal United States. It has the oldest archaeological records of any place inside of the boundaries of the United States and North America. And I think one of the things that's also really amazing about it is that one of the oldest examples of the first weapon is the Clovis Point, is just really close to Los Alamos. And I think it's really weird that just like this weird spot on the opposite end of the world from where most people live, where all humanity used to live, we find the world's first weapon, and then we find the world's biggest, sort of the last weapon. I think that's
It is absolutely beautiful. That is really cool. And another really a great point that you're kind of hinting at here, and something that we've talked about throughout the entire episode, just like nonchalantly, is that we're just measuring these things. We're finding these things. We're observing these things, but a lot of the why is kind of hard, right? The question of why is hard. And that's I don't know if that's more philosophy, but I mean, science can explain it, but man, the why questions are definitely the toughest questions, I think.
Yep.
Yeah.
Mhm.
Well, Kevin, it has been absolutely wonderful having you on the podcast. I'm glad that we finally got to do this. And I hope people out there are going, wow, there's a lot to be done in particle physics. Maybe I should get involved. Or, maybe they have some new ideas, or maybe a different perspective about nature. Really.
Yeah. If anybody wants to ask me anything, like Twitter, KP Hickerson, so you can find me, KP Hickerson on Twitter. So
Yeah, I mean, you can go to your website. I'll make sure that I link that and I throw that into both the intro and outro.
KevinHickerson.com. Yeah, I
Yep.
bought that for some reason.
All good. All right. Well, Kevin, thanks for being on the podcast. I really appreciate it.
Thanks for having me. It was really fun.
Awesome. Well, cheers. That is all for this episode of Everything STEAM. I just wanted to take a quick second and thank Kevin for sharing his knowledge and expertise about particle physics. The best way to access his social media accounts, research, and podcast is to head to kevinhickerson.com. I would also love to mention my amazing team for their collective efforts to make this show happen. This podcast was edited by Ariel Piermont, QC'd by Panyapit Eriksit, and our episode art was created by Gabrielle Edmiston. After the episode, please give our podcast a rating and review on whatever platform you get your podcasts on. We're always looking for feedback, and the rating would greatly help us out in the fight against the algorithms. Lastly, be sure to check us out on the socials for podcast news, upcoming episodes, and fun STEAM content. Just search Everything STEAM on Instagram, TikTok, Facebook, and Reddit to join in on the fun. Once again, thank you for listening to Everything STEAM. I'm your host, Sam Stanford, and as always, stay curious.